And just want to remind you guys that homework number 1 is due on Friday. We're going to cover that last section that's in that homework of 12.4. We're definitely going to get through that today. I'm hoping then that we also can get into 12.5, but we'll see how things go. But just a reminder. Okay. Are you guys at Lafayette able to hear me okay today? Okay, great. All right. We're going to cover, we talked about the dot product the last time. That's an operation that we can do with two vectors. And what we get from the dot product is we get a number, a scalar. It also tells us about the angle that's between two vectors. It can tell us whether the vectors are perpendicular to each other. If their dot product is equal to 0, then they are perpendicular to each other. Today we're going to talk about a different kind of product. This is section 12.4, and it's called the cross product. Now what we get here, instead of a scalar, what we get from the cross product is we get another vector. Okay, so what this purpose of this is the following. Say we're given two vectors, and we're talking about three-dimensional. So let's say A sub 1, A sub 2, A sub 3, and let's say B sub 1, B sub 2, B sub 3. We can find a vector that is perpendicular or orthogonal to both of those vectors. We can find a vector that is perpendicular, so I'm just going to draw that symbol there, perpendicular to both of the vectors. All right, and when we start talking about planes, this is going to come in very useful. All right, so this is the cross product. This vector is the cross product, and here's the definition of it. Definition, A cross, so it's like a times multiplication symbol, except it's not the dot, it's the cross, okay? Cross product is equal to the following three-dimensional vector. And now this is a very simple formula to immediately be able to memorize. A sub 2, B sub 3 minus A sub 3, B sub 2. That's our first component. Our second component is A sub 3, B sub 1 minus A sub 1, B sub 3. And our third component is A sub 1, B sub 2 minus A sub 2, B sub 1. And of course, that's just immediately what you would think it would be. Okay, so I'm hoping you realize I'm tongue-in-cheek here with saying that this is an easily memorizable or whatever formula. You can prove algebraically that this vector with three components is perpendicular or orthogonal to both A and B. So and we're going to get a much easier way to obtain this than what is written right here. Okay, all of these A's and B's, of course, are the components of the vector A and the vector B. First of all, I want you to note that this is a vector. It's not a scalar. It has three components to it. Second of all, it's perpendicular to the vector A, and it's perpendicular or orthogonal to the vector B. And the fourth thing is that this cross product is only defined for vectors with three components in three dimensions. Only defined when A and B have 3 components. Okay. Now, we don't want to be trying to memorize this formula. So the way that we're going to be obtaining a cross product of 2 vectors is by using the concept of what is called a determinant from algebra. So we might have to do a little walk down memory lane here about determinants, all right? So those of you who this is secondhand knowledge, just bear with me, all right? So I'm going to put here recall from algebra that we can have determinants of a 2 by 2 matrix or a 3 by 3, and of course we can go on from that. We know that a matrix is a selection of objects that have rows and columns. That's a matrix. So recall from algebra that the determinant, D-E-T-E-R-M-I-N-A-N-T, determinant of a 2 by 2 matrix, 2 cross 2 matrix is, okay, let's look here. Let's say the components or elements of the matrix are A, B, C, and D. 2 by 2 matrix. By the way, when we are talking about the determinant of a matrix, we don't use brackets here. We use these vertical lines surrounding the elements. So this is how a 2 by 2 matrix determinant is defined. You take the product of the down diagonal elements, so that's A times D, and then you subtract the up diagonal product minus B times C. And this is a number. So for instance, let's just look at a simple 2 by 2 matrix, 2, 1, minus 6, and 4, 2 by 2. Finding its determinant, we multiply 2 times 4 together, that gives us an 8, minus, and then we multiply the up diagonal. So that's, careful with the minuses, this is minus 6 times 1, so that's a negative 6 up diagonal product. We end up with a double negative, and we have a determinant that's equal to the number 14. Does this ring a bell at all from algebra? Okay. Now, what we're going to be looking at, though, are 3 by 3 determinants. So determinant of a 3 by 3 matrix. And this is what we're going to end up using in order to get the cross product. So first of all, I just want to give you the general formula, and we're going to go through an example. So say we have a 3 by 3 matrix. Let's call the elements A1, A2, and A3. This would be, we can call this the first row, all right? And we have our vertical lines on either side. And then we have B1, B2, B3, and then finally C1, C2, and C3. So this is the 3 by 3. Okay, now I'm going to show you one way to get the determinant. It is true that there are other ways to get the determinant, but I'm just going to show you one way. All right, what we do here is we go across the top row. And we start here with the first element in that top row, which in this case we're calling A sub 1. What we visually do here with this element, we write whatever the element is, and we're going to multiply it by something. What we do visually is we cross out that first row and the first column. So what we are looking at then is a 2 by 2 matrix of the other 4 elements that haven't been blocked out. And we're multiplying this element then by that determinant of that 2 by 2 matrix. Okay, that's our first step in the determinant. Now we go around to the second element in the first row, but we have to put a minus sign in front of it. Minus, and then we write the second element. And then what we do then is, again, visually, we still cross out that first row, but this time we also cross out that second column that contains that second element. We're still left with 4 elements, and we're going to multiply that minus A2 by the determinant of those 4 elements. So that's going to be minus A2 times the determinant of B1, B3, C1, and C3. Okay, we're 2/3 of the way through. Then we have to finish off our first row, and now we'll just put a plus A sub 3, our last element in that first row, and we're going to do the same thing again. We're still crossing out mentally that first row, and now we're crossing out the last column. And then we have those 4 elements. We're going to multiply that element by the determinant of those 4 elements. So that's B1, B2, C1, and C2. All right. Now what we are going to do then is now we've got numbers multiplying 2 by 2 matrices. So we've already seen how to do the 2 by 2 matrices. So that's where we're going to proceed next. So we start back with the first element there, A1, and then what we're going to be multiplying it by is the determinant of this B2, B3, C2, C3. Now that's the down diagonal product, B2, C3, minus the up diagonal product, I'll say B3, C2. I'm just multiplying in a different order. Then we go to our minus A sub 2, and again we're going to be multiplying that by that determinant of the 2 by 2, B1, C3, the down diagonal, minus the up diagonal, B3, C1. And then finally we go to plus A3, and we're going to be multiplying that by the determinant of B1, B2, C1, C2. Down diagonal product, B1, C2, minus the up diagonal, B2, C1. All right. Okay. And when you compare them, if you FOILed this thing out and distributed this whole thing, then that's where you get the determinant here. So basically, this ends up being a number. Okay, that you get. So let's just look at a 3 by 3, and then we're going to see how this. Then we're going to look at how this relates to the cross product. So let's do a concrete example here. 1, 2, minus 1, 3, 0, 1, minus 4, minus 5, 4, and 2. 3 by 3, we've got the straight lines there. We're going to do its determinant. Okay. So we go across that top row. My first element here is 1, so I write that down. Then I'm going to put some parentheses here because I'm multiplying it. All right. Well, actually here, let me not go too fast here. Let me first just put the 1, and then we're going to multiply it by a determinant. We cross out the first row. We cross out the first column. So the determinant is going to be of the matrix 0, 1, 4, 2. Okay. And then we'll do another step after this. Then I go to my second element. Now, it's very important to remember you have to put a minus sign in front of the second element. So that's going to be minus 2. If 2 were a negative 2, that would be a minus 2, a double minus. And then I'm going to multiply that second element. Then, again, I'm going to cross out the top row and the second column. And I'm going to have the determinant of 3, 1, minus 5, and 2. Okay. And then finally, we have our last element, which is a -1 plus the -1. And then we multiply that by the determinant of what? Again, crossing out. Now this time the third column, and again the first row, the determinant of 3, 0, -5, and 4. Okay, so now we'll figure this out. So we have 1, now I'm going to have my parentheses here. We have these determinants. 2 times 0 is 0, minus, so we have 0 minus 4 times 1, which is 4. So we have 1 times -4. Then we have -2, and so what do we have? 3 times 2 is 6, and so don't write the minus yet. We have minus a -5. So I'm just going to write +5 right here with a double minus. And then we go to our last element, -1. Down diagonal, 3 times 4 is 12. And then up diagonal is going to be 0 because we're multiplying by a 0. Okay. All right.
On the end, shouldn't it be like +1?
No. We only put the minus in front when we do the second element. Only the second element. That's why I said if that 2 had been a -2, we would have ended up making it a +2. But that first and third element, they don't change signs. Okay? All right. So then we just figure out what this all comes to. So this is going to equal what? -4 minus 2 times 11, that's -22. -1 times 12 is -12. So 26 and 12, we end up with a -38 for our determinant. Okay? All right. Now, how does this relate to the cross product? What we do with the cross product is this. That very top row is going to be those unit vectors I, J, and K. Okay. So I, J, and K. And then the next 2 rows are going to be our 2 vectors. So in this case, we're talking about A1, A2, A3, B1, B2, and B3. And we've got the straight lines there because we're doing determinant. Okay. We again are going to go across this first row. So this is going to equal, okay, our element here is I, the unit vector I. Okay, what do we need to cross out? We need to cross out that first column in the first row, and we're going to be multiplying it by the determinant of A2, A3, B2, and B3. So what we're going to, so let me just do this right here. A2 times B3, that is the down diagonal, minus the up diagonal, which is B2, A3. Close our parentheses. That's going to be the component of the first element in our cross product. Then we go to our second one. Now this is the one we have to put the minus sign by. Minus that J unit vector. And then we figure out what we're going to multiply that by. Again, we're going to cross out that first row and now the second column. So it's going to be the determinant of A1, A3, B1, and B3. So we multiply those together. A1 times the B3 minus, and then it's going to be minus the B1 times A3. And then finally, we go to our last element in the first row. We're going to be back to a plus sign here, plus K. And we're going to be multiplying this by what? Let's cross out the first row again, and now the third column, and it's going to be the determinant of A1, A2, B1, and B2. So that's A1 times B2 minus B1 times A2. All right. If you compare, and so what this really is then, that is looking at it in terms of I, J, and K. But we know we can also write a vector just looking at the components with these angle brackets. So this becomes, our first component then is A2B3 minus B2A3, comma. Our second component, we're going to be applying the minus sign here to both of those terms there. So they're going to flip, and I'm going to have B1A3 minus A1B3. And then my third component is going to be A1B2 minus B1A2. And if you compare that with what I had written at the beginning, they're identical. So let's do a concrete example of given two vectors finding its cross product. Okay, example. Say we're given that A is equal to the vector 1, 3, 4. B is equal to the vector 2, 7, and negative 5. And we're asked to find A cross B. All right, so we set up our 3 by 3 matrix. The first row is going to be the I, J, and K. And then you have to write these, if A is whatever the first vector is, needs to be written on the second row. You cannot just arbitrarily switch these. So I write 1, 3, 4 because it's A cross B, and then I write 2, 7 minus 5. Okay, so we go through this process here. Equals. All right. Going through that first row there, I start with my I, and let's see what I'm going to be multiplying that by. Okay, crossing out my row and column, my determinant there is going to be what? 3 times minus 5, that's negative 15. Let me put in the minus sign right away, because remember I have to subtract the up diagonal. And then it's minus 7 times 4 is 28. And then let me close the parentheses. I'll combine those numbers in just a minute. Then let me go to the J. Again, it's got to be a minus in front of the J. And let me cross out my rows and columns. So, what do we have? We have 1 times negative 5. So that's negative 5 minus 2 times 4, 8. All right? And then we go to our last component, plus K. And again, cross out the appropriate rows and columns. We have 1, 3, 2, and 7. So we take 1 times 7 is 7 minus, put that minus down right away, 2 times 3 is 6. Okay, so now we just simplify our numbers here. So this ends up equaling what? 15 and 28, that's a minus, that's going to be minus 43 times the I vector. Now be careful here, we've got that negative business, minus in front of the J, so we've got to distribute that. So that's going to be a negative, negative 13. So I'm going to be a double negative. I have 13 times positive 13 times J. And then we have 7 minus 6 is 1 times the K. Okay, so again, this is one way to write a vector in terms of the I, J, and K. This is also equivalent to, in the angle bracket, minus 43, comma 13, comma 1. All right. Now, it's always a good idea to just double check quickly that this is indeed orthogonal to both of these. So how can I check algebraically? We're not going to be drawing any pictures to figure this out. How can I check that that is orthogonal to my two initial vectors? Take the dot product, and if the dot product is equal to 0, it's orthogonal, okay? So, let me just put this recall here from the last time. Recall, A is perpendicular to B if and only if A dot B is equal to 0, all right? And we know the dot product is multiplying the corresponding elements together. So if we look at this, let's just look at this one here. Minus 43 times 1, so that first product is minus 43. Then we take our second elements together, 13 times 3, that's 39. And then our third elements together, 1 times 4 is 4. When we combine those numbers, we get a 0. So the dot product is indeed 0. Meaning I didn't mess up on my arithmetic, right? That's the big thing as to why you should check it. Let's just check the other one then. Minus 43 times 2, the first component, that's going to be a minus 86. 13 times 7, that comes out to 91. And then finally, 1 times negative 5 is negative 5. And so those three numbers again combine to 0. So we know we're fine. We got the right cross product. Okay? So does everybody have the general idea here as to how we get the cross product? All right. So there are some properties that the cross product has. One of them is this, and we'll show this, that if we take any three component vector and we cross it with itself, what we're going to get is the 0 vector. Remember, we get a vector, and this will be the 0, 0, 0 vector. And we could actually show this very quickly. I think I'll do it. I, J, and K. Let's say A is A1, A2, and A3. And remember, we're repeating it. We're taking the cross product with itself. So I repeat those elements. And then I go through my determinant here. So we go through that first row, I, and then I'm multiplying I by this. Crossing out my rows and columns, I have A2 times A3, the down diagonal, minus, and then my up diagonal is also A2 and A3. So we see right there, I get a 0 for that first element. And if I do that for the other two, I will also get zeros. So I'll get a minus J times 0 and a plus K times 0, and everything will zero out when I do the determinant. So therefore, so we have this fact that A cross itself is equal to the 0 vector. Okay? I'll put a little asterisk by that. All right, so a couple other things we have, and we know that it gives us, the cross product gives us an orthogonal perpendicular vector that's perpendicular to both of the starting vectors. So we have this. A cross B, we know, is orthogonal to A. A cross B is orthogonal to B. So therefore, the dot products are 0. Thus, the dot product of A cross B with A is equal to the number 0 because they're orthogonal. And A cross B dotting it with B is also going to be 0, a scalar. So those are, right here, are a couple of other properties, those last two that I had written there, that you should be familiar with. All right. Now, so far, we've been just looking at this cross product pretty much just using algebra. All right. We've just been looking at combining numbers, doing determinants, just looking at it algebraically. Well, we can look at this cross product also in a geometric kind of way. And one thing we can get is the length of the cross product vector. So let's look at the length and the direction of A cross B. So this is much more geometric than what we have looked at so far. All right. Now, I'm not going to prove this, but this is the fact about the length. If theta is the angle between the two vectors, is the angle between A and B, so in other words, we have A and B, let's see, A cross, let me do it this way. Let's put A down here and B here. I'll explain that stuff in just a second. So that's if we join them at their tails, that's the angle between them. And we're assuming here that this angle theta is between 0 degrees and 180 degrees. So theta is between 0 and 180 degrees, or 0 to pi. All right. Then the length. So I'm putting the lines here to indicate that we're talking about the length of the vector, the length of the cross product, length of the cross product is equal to the following. It's equal to the magnitude of the A vector times the magnitude of the V vector, but this time, oops, okay. I'll get to that about the order of operations. The question here is about the order of operations with the cross product and dot product, and I'm going to get to that in just a minute, okay? Let's go back here. All right, the length of this is the length of A times the length of B. So this is very similar to what we saw with the dot product, okay? But now it's being multiplied by the sine of the angle theta, not the cosine as we had seen before. All right? Now, notice here that since theta is between 0 and 180 degrees, so let's look at our 4 quadrants here, 1, 2, 3, and 4. It's in this first and second quadrant, the sign is positive in both of those quadrants. So therefore, we don't end up with a negative length here. The sign is going to be non-negative. Okay, so you certainly need to remember this, so let's put asterisk there by that. So that has to do with the length of the cross product. Now the direction is found using the right-hand rule. Direction is found using the right-hand rule. Okay, so let me get something up here. And we had seen the right-hand rule with the X, Y, and Z axes. I think that was like the first day of class. But let's look at this. Okay. So basically, if we have the vectors A and B right here, those are the blue lines there, and we're doing a cross product. A is first, B is second, and we have the angle there between going from A to B. That's the angle theta, all right? So basically, we take our right hand and we put it then in, we curl our fingers around from A to B. So here A and B is going this way, so I curl my fingers this way with my right hand to represent from A to B, and then the direction of my thumb is the direction that the perpendicular cross product is going. So in this case, the cross product is going up like this, all right? Now, if I had, let's look here, let's look actually at this one right here. Oh yeah, sorry guys. Let's get this down. All right, let's look at this one right here. Let's just say this is our configuration of A and B. And we're looking at A cross B. So I need to be going, let's see, well that'll work. We have A, and then we're going A to B, and the cross product will come up out of the paper, all right? Because the angle between 0 and 180 degrees, we're going in that direction, so it goes up. But what if I had this? What if I had B here and A here, and this here was my angle between them that was less than 180 degrees. And I want to look at the direction of A cross B. So here, I have to do a little contortion here with my hand. Here I'm going to be going from A to B this way, all right? And so, oh, I just got a cramp. And so my thumb then is going down. And so my direction of the cross product is down into the paper. We start with whatever the first vector is, do the angle to the second vector, and follow our thumb. So sometimes we have to be going like this. So A cross B here goes down into the paper. All right. Okay. So let me just put something about this just down here for the right-hand rule. Basically, we curl the fingers of our right hand in the direction from A to B. In the direction from A to B. This is where the angle is less. We want to make sure that angle is less than 180 degrees. Then the thumb points in the cross product direction. Then the thumb points in the direction of the cross product. In the direction of the cross product. That's the right-hand rule. All right. Okay. So I have something else up here that I want to show. And let's get that up. Okay. All right, so let's see. Does this indicate, okay. Let's see, A stays fixed. All right, so the red arrow is A, the green arrow is B, and the blue arrow perpendicular is the cross product. So here we see that so we're doing red arrow cross green arrow is what we're doing. Notice as long as the angle here is less than 180 degrees, using the right-hand rule, it's going to be going up. All right, the cross product is going to be going up. Now, as we then have the green ones start to get further and further away from it, first of all, notice this, that the cross product, the length of it starts to shrink quite a bit. Because remember, the length is the magnitude of A, oh, you can't see that. The magnitude of A times the magnitude of B times the sine of the angle between them. Well, once that theta gets close to 180 degrees, we know the sine of 180 degrees is 0. So sine's getting very, very small, so the length of the cross product starts to shrink. Once we actually get to pi, we don't even have a cross product anymore. It's 0. All right? Then, if we're still doing red arrow cross green arrow, now with the right-hand rule, we now have the smaller angle is now over on this side. We're doing, this here is our smaller angle, so we're going from the red cross green, so we're going this way with our right hand, and now it's pointing down. Okay. Does this make any sense? Make sense? Jenna? Make sense? You're reserving comment? All right. Okay. Notice the cross product reaches its maximum length there when we're at an angle of 90 degrees between the two, because the sine of 90 degrees is 1. So we have the biggest magnitude there. Okay? So we're not tremendously impressed with our little TEC things here that's given by our publisher. All right. Okay. All right. We're getting to that question there that you guys had asked. So one thing we want to notice here is that, oops, where are we here? One thing I want to say is this, that A cross B, if we change the order, A cross B is the opposite of B cross A. So we cannot, if we switch the order, it's going to make it a vector going in the opposite direction. So we can say B cross A is in the opposite direction of A cross B. All right? Okay. All right. I think then while we're at it here, let me just go through a couple of other of these. So this is one. Let me label this number 1. I'll call these other facts. Okay. So A cross B equals minus B cross A. And then number 2 here, if we take A and we cross it with B plus C, where we're adding the two vectors together, then this does distribute. This is equal to A cross B, where we distribute, plus the A cross the C. So it does distribute. All right. And similarly then, if we do A plus B vector, and we're crossing that with the vector C, it also distributes. But this time it's going to be A cross C. We've got to be mindful of the order plus B cross C. Again, it will distribute. All right. Let me see here, because I know that they were asking. I didn't write this down. Okay. All right. One thing, so let's go to number 4 here. Let's just look at what happens when we cross those unit vectors together. Remember that I is equal to 1, 0, 0 vector, J is the 0, 1, 0 vector, and K is the 0, 0, 1 vector. So we can show this. You can just show it out just using the determinants that we did. We can show that I cross the J is going to give us the K vector, all right? And that is perpendicular to the I and the J. So in other words, here, here's X, Y, and Z. So we have I in the X direction, that unit vector there. Y, J is in the Y direction. So here's our I, here's our J. And when we cross those, you can see using the right-hand rule, we're going to get that vector that's perpendicular to both of them in the Z direction, which is the vector K. Similarly, we can show that J cross K is equal to the I vector. And lastly, the K cross I is equal to the J vector, right? Okay. Let me just get this part out of the way here with this, because this was the question that came up. I'm going to defer that. I will put this one thing down, because I'm not even going to cover this, but this comes up, this applies to the question that you asked, Lafayette. So I'll just put this as an FYI, all right? A cross B cross C. So we take the cross of B and C, and then we take A cross that. That's equal to the following. A dot C, the dot product of A and C, you can see I don't have this memorized, times the vector B minus the dot product of A dot B times the vector C. So I'm certainly not going to hold you guys to remembering that. There's one other relationship that I'm going to talk about in just a couple minutes, but I hope that's what you guys were referring to. All right. I think these are pretty much common. Getting back to these other facts here, this is pretty much just easy to remember if you just distribute it. This, you have to remember that if you reverse the order, you do have to take the negative of it. Okay. Now, I want to do one problem, and then we'll take a break here. I want you guys to remember this. If we're talking about a straight line, how many points determine a straight line? Well, we have an infinite number of points on a straight line. But in order to figure out what the straight line is, how many separate points do we need? 2. We basically only need 2 points to be able to figure out what the straight line is, okay? So 2 points determine a straight line. 2 points determine a straight line. All right. Now, let's go then to a plane. A plane is like a cookie sheet that extends out forever, okay, that doesn't bend. It's not a flexible cookie sheet. Just view it. It just goes out forever in 2 dimensions all the way out to infinity, all right? So basically, you want to consider the entire universe. Every plane cuts the entire universe in half, or something like that, all right? Because it just extends out forever. So similar to this 2 points determine a straight line, we have this. 3 points determine a plane. All right. Now, you guys there can't see this, but what I have here is I have 3 little colored sheets of paper here that represent a dot, a point, in 3-dimensional space. One there on the board, one up higher on that wall, one down lower on the back wall. 3 points. Those 3 points, so if we just consider, of course, that they're infinitesimal little points rather than 2x2 Post-it notes, all right? Those 3 points, if we connect them with a triangle, we can then extend that triangle out infinitely into space, and these 3 points determine one single plane. All right? Does that make sense? We have to have 3 of them. 2 isn't enough. 4 can be too many. But 3 is just right. That's a Goldilocks tale, all right? 3 is just fine. They form a triangle in space, and we can extend that triangle out. All right? Now, if I then have a 4th point, and let me just stick this down here. So now we have 4 points in space. Well, if we take any 3 of those 4, we can do a triangle and get a plane, right? If I do this one, that one, and that one that I just put down there, that we're going to extend out to a plane. If I look at my original one, that's that, and the other one, that's also a plane. But notice the particular 4 points that I picked here won't all lie, all of them will not lie on the same plane. You see that? So 4 points don't necessarily lie in the same plane. Now, if I took this point here, this extra one that I added, and let's say I decided, I don't know, maybe to stick it up here somewhere in space, well, maybe, I don't know, I should have brought some string with me too. This point then might be on part of that triangle that we originally had, all right? And so, yeah, we can have 4 points that are on the same plane. Because any single plane contains an infinite number of points. But my point being, no pun intended there, is that 4 points don't necessarily have to be on the same plane. But 3 of them absolutely will be on the same plane. Okay? All right. I think we'll take a 5-minute break, and then I'm just going to do some more work stuff with that algebraically. Okay? Oh, problems, problems, problems. What did I do now? Okay. All right. Two things. Sorry. Couldn't really see my little demonstration. Also, did I answer your question about the dot and cross product? Okay. Why don't you put that in an email? Be more specific about exactly what you want, and I can address it. The answer was no. I did not answer their question. Okay. So let's look at this type of problem here. We're given 3 points, P, Q, and R, and we're asked to find a vector that's perpendicular to the plane that contains those 3 points. So we know that there is a plane that contains these 3 points. So let's just, basically we're going to have something that goes out in all directions. Okay, there's a plane that contains those 3 points. What we're asking for is a vector that is perpendicular, forms a right angle with the plane. All right. So what we have to do here with this, we're given 3 points. So given 3 points, we can take a direction or a displacement vector between any pair of those 3 points. And so we can obtain 2 vectors that are on the plane, all right, given the 3 points. And then using those 2 vectors that are on the plane, I can then do a cross product and get a vector that is perpendicular to those 2 vectors. So let's do this. Let's form the 2 vectors. Now, when I say that these are on the plane, I'm being a little loose here. They're actually parallel to the plane. Remember, vectors just have direction and magnitude. So any one vector can be floating around in all kinds of different places. So when I say it's on the plane, I really mean it can, if it were on, it could lay flat, parallel to the plane, if it were decided to land on the plane. All right. See what I say? So let's form the 2 vectors. Let's form the displacement vector between P and Q. So we take our Q components and we subtract the P components. So that's going to be -2, -1, 5 -4, and -1, -6. Oops, -1, -6. So that vector turns out to be what? -3, 5 and 4 is 1, and -7. So that's one vector that lies on the plane. And then let's do a P and R. Look at that displacement vector. So we take R components and subtract the P components. 1 - 1 is going to be 0, of course. -1, -4. 1, -6. So this vector then is, let's see, 0, -5, and also -5. -5 and -5. All right. So these are our 2 vectors that are on the plane, and we're going to get the cross product. So now we're going to find PQ, that displacement vector, cross the other one, cross PR. So we do our determinant business here. IJ and K, PQ is going to be -3, 1, and -7. And PR is 0, -5, and -5. Okay. Okay, go through the first row there, and so we write down I, the I vector, and we're going to be multiplying that by the determinant. Let's see, we're going to have -1 times -5, -5. Now here, just be careful, get used to kind of combining things. We're going to have a minus, but notice what I'm multiplying together, -5 times -7, so I'm just going to write that as a third positive 35, all right? Then we have minus the second component, that's minus the J. Let's cross out that row and column, and now let's see what we have here. -3 times -5, that's going to be a 15. Then we put a minus, and then we have 0 times -7. So that's a 0, -0. And then we have plus K, and let's see. -3 times -5, that's going to give us a plus 15. And then, again, we're going to have a -0. So the cross product here, then, I like to end up writing things just with the angle brackets. Our I component is going to be -40. Our J component, now don't forget, I've got that minus in front that I've got to carry over. I've got to distribute. It's going to be -15. And then the K component is a positive 15. All right. Now this then, we can then go and check that this vector here is indeed, or has a dot product of 0 if I dot this with either of my 2 vectors. Now, Okay, this is the vector we get. And this vector then is perpendicular to our plane. What other vectors, plural, I guess I could say, could I also say are perpendicular to that plane? Because there's certainly not just going to be one single vector that is perpendicular to that plane. Is there anything common with those three components, 40, 15, and 15, that I could work with to maybe lighten my, if I have to do some further arithmetic, to lighten my load, so to speak? Divide by 5. They're all divisible by 5. Remember, I can multiply all the components of a vector by a scalar, and it's still going to go in the same direction. It's just going to be a smaller, in this case, a smaller vector. So I could do or minus 8, minus 3, and a positive 3. That's also going to be perpendicular to our plane. We understand that? It's just multiplying everything by a scalar. Okay, so that's another vector that's perpendicular to our plane. Can I, yes, Jenna?
Can you, like, choose different letters? Like, can you do QR?
Oh, could I have done originally? Absolutely. Instead of picking PQ and PR, I could just as well have picked, say, QR, and I could have picked PQ and QR. All right? I could have done it that way. So does that answer your question? Mm-hmm. What else? Or, now I can no longer divide by a number to get it unless I want to deal with fractions, but what other thing could I do with a vector? Multiply by scalar. What's one scalar I can multiply by? What's an easy scalar? 0 won't give me anything. That just gives me the 0 vector. How about minus 1? If I multiply everything by minus 1, I'm basically flipping the vector from one direction, reversing its direction. So I could say also positive 8, positive 3, negative 3 is also going to be perpendicular to our plane. I'm just flipping the direction of it, okay? So here I'm multiplying by negative 1. Or a very non-technical thing, reversing its direction or flipping its direction. All right. I just want you to realize there isn't necessarily just one single answer for some of these things. All right. So that's kind of problem. We were able to find at least one vector that was perpendicular to a plane where we're given 3 points to determine a plane. I want to give you another fact here that I want you guys to remember. 2 non-zero vectors, and as I said, unless I'm specifically talking about the 0 vector, you can pretty much assume that we're talking about non-zero vectors. 2 non-zero vectors, A and B, are parallel. If and only if A cross B, their cross product, is equal to the 0 vector. So this is something that I want you guys to remember. So 2 vectors are parallel if and only if their cross product is equal to 0. All right? Now remember that the magnitude of the cross product is equal to what? The magnitude of A times the magnitude of B times the sine of the angle between them. Now, if vectors are parallel, the angles between them are either going to be 0 degrees, if they're both going in the same direction, all right, Or if one of them is being flipped, the angle between them could be 180 degrees, and they're still parallel. So therefore, when they're parallel, theta is either equal to 0 degrees, or it could be the flip of that 180 degrees. In either case, the sine of both of those angles is equal to 0. So therefore, their cross product is going to be 0. So that's an interesting set of facts here. Let me just kind of look at this here with the dot product versus the cross product. With the dot product, if their dot product is 0, then they're perpendicular. So A dot B equals 0 if and only if they are perpendicular. But A cross B is equal to the 0 vector if and only if they are parallel. And one way of putting parallel is just those two kind of parallel lines like railroad tracks. So that's a contrast between the dot product and the cross product. So let me definitely mark that. Now, we're continuing here with some geometric stuff here. So let's say we have a vector B, and let's have another vector A, like this, and let's have an angle between the two of them. We'll call it theta. Now let's complete this as a parallelogram. So we want to continue with a line that's parallel to the bottom line there, and a line over on this side that's parallel to the line on the right, and we can get a parallelogram. Now the thing is, there's an interesting fact here that the area of this parallelogram is equal to the magnitude of the dot product. The area of this parallelogram equals, well, let's see what it equals. Let's go back to some basic geometry. All right. It's going to be the length of our base, so that's the length of the B vector, times, when we draw a line down perpendicular to the base, times the height of that line that we draw down as a perpendicular. Well, let's look at this. Let's find out the length of that line that we drop down. The length of this line here, of course, is the length of the A vector. That's the length of that. We can consider that like a hypotenuse. So how would I represent, with using trigonometry, the length of that vertical line that's hitting the bottom at a right angle? Remember, our angle over here is theta. We're calling it theta. So what's the relationship between the opposite and the hypotenuse? What trig function are we going to look at? We're going to look at the sine, right? The length here is going to be the length of our hypotenuse, which is the magnitude of the A vector, times the sine of that angle. Remember, the sine is opposite over hypotenuse. All right? But we want to make sure that we're never talking about a negative height. So we want to put absolute values there around the sine. Because if this angle were bigger than 90 degrees, no, I'm sorry, sines opposite, well, that would still be okay. Never mind. Yeah, sine is still going to be Yeah, never mind. Never mind about that. That doesn't have to have absolute values. Just the sine of theta, because that's still going to be positive no matter anywhere between 0 and 180 degrees. So let's look at this. The area of this parallelogram then, that's the length of that base, the magnitude of B, times the magnitude of that height, which is the magnitude of A, times the sine of that angle theta. Well, that's exactly the formula for the length of the cross product. All right, that we had seen earlier. So basically, let me just summarize this as a fact. The length of A cross B equals the area of the parallelogram. Formed by A and the B. All right, so that's the fact there. All right. Now there's another thing that we can do here. It'll actually kind of use this fact to look in 3 dimensions. Because right here, this is really just a 2-dimensional looking parallelogram. It's in 2 dimensions. Let me introduce something that's called the scalar triple product. It turns out it's going to be a scalar. It's going to be a number. So let A, B, and C be 3-dimensional vectors. Then we take A and we dot product it with the cross product of B and C. So we take A dot B and C. So we're going to end up, because it's a dot product, we're going to end up with a scalar, with a number. This actually is going to equal this. A1, A2, A3, B1, B2, B3, C1, C2, C3. It's going to equal, this dot product is going to equal the determinant of this 3 by 3 matrix. Determinant of the 3 by 3 matrix formed by A, B, and C. Okay. And this has a geometric interpretation to it. It's called the scalar triple product. I just want to say this, that fact, A dot B cross C is the same as, it turns out to be the same number as A cross B dot C. So we can switch the order of operations of the cross product and dot product. But let me show you what this scalar product shows geometrically. All right. Right. Triple product. Okay. So here we're looking at, we have 3 vectors in A, B, and C. So here is our B vector, this one red arrow. Here's our C vector. And going up here is our A vector. So 3 vectors, and we're just joining them all at their tail. Okay? Now, what we get here when we extend out in 3-dimensional space, we can complete what's called a parallelepiped, where we make it into it looks like a big cardboard box that's starting to tilt over, okay? It's like a parallelogram, except it's in 3 dimensions. It's called a parallelepiped. And these 3 vectors, if we extend them out like this, actually can be considered to be forming this figure. Now, the area of the base of this thing, right here, this is the base of it, we've just shown that this area here is equal to the length of the B cross C vectors here. So the area of the base is, we'll call it capital A for area. It's the length of B cross C. All right. Now, with parallelepipeds, it's very similar to a parallelogram. The volume of this is equal to the area of the base times the vertical height. All right? So to get our vertical height then, we use our A vector here, and we then are looking at this angle. Let's see, we have the angle, basically the angle, okay, here's B and C. We have their cross product, which goes, remember, cross product is this blue vector. It's going perpendicular to C and B. And then we look at, we have this vector A that's going at an angle upward. To get the vertical height, we have to multiply that length of that hypotenuse by this time by the cosine of the angle between A and the cross product. So this height here, this perpendicular height, is equal to the magnitude of A times the cosine of the angle between the cross product and A. And this is where we have to put a absolute value around the cosine because we want it to be a positive number. Okay, so the volume then is the area of the base times the perpendicular height. So it's magnitude of A times the magnitude of the base, B cross C, times the absolute value of the cosine. And then this is equal to the magnitude of the dot product. It's the magnitude of the first vector, magnitude of the second vector, times the cosine of the angle between them. So it turns out that that volume is really the cross product of those 3. So let's put it this way here. Oh, yeah, I keep doing that. See, I'm using this a lot more than I did before. Okay, thank you. So basically, we can say this, that A dot B cross C, the, what do we have to say? We have to say the absolute value of that is equal to the volume of the parallelepiped, parallel, and then P-I-P-E-D, formed by A, B, and C. All right. Okay. So that's called the triple scalar product. All right. So let's say that we have these 3 vectors, B and C, and then we have A coming up like this, for instance. All right. We know that their scalar triple product is going to give, we can kind of form this parallelepiped thing. Let's see here. Where? I have to go up like this. We end up getting this cardboard box thing. All right, but what if the area of that parallelepiped was 0? What if we did this dot product and we found out that the volume, not the area, the volume equals 0? Well, what that means is our cardboard box is basically crushed down to the ground, and all three of those vectors are on the same plane. They're all on the ground. C and B and A are all smashed down on the ground, and the parallelepiped is just a flat nothing, and its volume is 0. So this tells us the following then. Fact. If the scalar triple product of A, B, and C equals the number 0, then all three vectors lie on the same plane. And all three vectors lie on the same plane. All right. There's a name for that. It's called coplanar. C-O-P-L-A-N-A-R. Coplanar. All right. So let's do a concrete problem with this. And here it is. Let's say we are told to use example. Use the scalar triple product to show that A, which is equal to 1, 4, minus 7, B, which is equal to 2, minus 1, and 4, and C, which is equal to 0, minus 9, and 18, those three vectors, to show that they are coplanar, on the same plane. All right. Now, question. If I were only given two vectors, if I were given a vector A and a vector B, would any two vectors be coplanar on the same plane? Let's look at our 3 points here on the wall. We can draw a vector from, say, this one to that one, and a vector from this one, say, to that one over there. That's two vectors. Can they be considered to be on the same plane? Yes, they can. Because given 3 points, 3 points will determine a plane. So I can take, given 3 points, I can have two vectors. They're on the same plane. All right? But if we're given 3 vectors, there is no guarantee that 3 vectors are going to be on the same plane. Okay, I can't look at these numbers here on the components of these 3 vectors and just eyeball it and say, yeah, they're on the same plane. All right, I can't do that. But I can compute the scalar triple product, and we can see if we get a 0. And then if we get a 0, they're on the same plane. So let's do that. Let's take A dot B cross C, and all that is going to be the 3 by 3 matrix. We'll start with our A vector 1, 4, negative 7 in the first row. The B vector 2, minus 1, and 4. The C vector 0, minus 9, and 18. Got the straight lines. We're going to calculate the determinant. All right. So we go across on our first row here. We have our 1. And then we're going to be multiplying our 1 by the determinant of those 4 elements there. So that's going to be what? Minus 18. But I'm going to have a double negative here. That's a negative 36, but I have to be subtracting that. So that's a positive 36. Then I go to my next element here, a 4 in that first row, and remember that has to be a minus in front of that, minus 4. And then let's see what we're going to multiply this by. Okay, we have 2 times 8, that's 36. And then we have minus 0 times 4, so that's minus 0. And then we go to our third element, that's going to be the negative 7. And we're going to multiply that by, okay, we've got determinant of 2 minus 1, 0, negative 9. That's going to be negative 18 minus 0. Okay, so let's see what we get here when we combine all the numbers. 36 minus 18 is 18. 18 times 1 is 18. Minus 4 times 36 is what? Minus 144. 7 times 18 is, I think, 126, isn't it? And that's going to be a plus, 126. So we combine 126 and 18 is 144, right? So we end up with 0, all right? So therefore, since it's a zero triple scalar product, we then can conclude that they are all on the same plane.
Is it still part 1.4?
Yes, yes it is. Have I indicated yet the start of 12.5? That's right. Well, we've just now finished it, Nikesha. All right? All right? Okay. Now I'm just going to get started a little bit on, that's the end of 12.4, the cross product. So that's the end of stuff that's going to be, that's on the homework that's due on Friday. Figure you have enough time from now until then to be able to complete whatever you haven't already done on the homework. Okay, so therefore, I just want to get a little bit started on 12.5 because I don't want to be getting too far behind in the schedule. And there's just a couple of things that I can talk about here about 12.5. Okay, 12.5 is all about the equations of lines in space and the equations of planes in space, okay? So it's equations of lines and planes. Okay, so we're going to start with lines. Now, when you took elementary algebra with graphing, a line is, in two-dimensional space, a line is determined by a single point and the slope that it's going along. So let's just say in two-dimensional, a line, a straight line, is determined by a point x, let's call it x sub naught, y sub naught, that it goes through, that it passes through. And we need more than just a single point. Another piece of information we need to know is what's the slope of that line. So, and we need to know the slope. Once we know a point that's on the line and the slope of the line, we can obtain the equation of the line. If you remember this from algebra, we get y equals y naught, y minus y naught equals m times x minus x naught. That's that point slope formula. So we have to know a point, we have to know the slope. There's a similarity here now in 3 dimensions. A line in 3-dimensional space called a space line. In other words, it's just some straight line going from there to there infinitely, okay? Just little threads, all right, that's going straight through. A line in 3D, 3-dimensional, it's also determined by a single point that it goes through. And we'll call that P naught, X naught, Y naught, and Z naught. It has 3 coordinates. by a point it passes through, and, big letters there, and a direction vector that is parallel to the line. So a line is determined by a point and a particular direction vector that points which way this line is going. Of course, the line will also go in the other direction. So it's going infinitely from one point to another. All right? Big asterisk there because I want you to understand this point. And I know seems like I'm just repeating myself. A line is determined by a single point and by a given direction vector. Okay. And we can have three types of equations for a line in 3D. Just like we had in 2D, we had different forms of equations for a line in 2 dimensions. All right. The first one, and A, we can write the equation of a straight line as what is called a vector equation. And let me just write it down here. This is R is equal to R naught plus a variable t times a vector v. Okay. This vector v is our position, is our direction vector. T is our variable. It can go from minus infinity to plus infinity. R naught is a given position vector. This is our given point that is on the line. Okay. Let me just show you this little display here on this. And all right, vector equation of a line. So notice here, this L here is our straight line, this dark line right here. And we have a single point that's on the line. Now, we're representing, this is a point that's on the line, but we're representing that point as a position vector. Remember, given any point, we can let the vector from 0 to that point be a position vector. So therefore, R naught here is our position vector of our given point. Now, t can go from 0 to have positive values, negative values. Now down here, this dark black vector down below that is parallel to the line, that is our direction vector, all right? So basically, we're going from this point here, and depending on what our value of t is, we're going to then be adding on a multiple of this direction vector, which is parallel to this line. So these blue arrows here point to new points that are on our line for various values of t. For bigger positive values, it's going to go further out on our line in this direction. For t equals 0, it's going to be right there on that point. Now, if t is negative, we're now going to be going in the opposite direction and going the other way from our point. So this is one way to represent the equation of a line, all right? So, Okay. Just one other thing, and then I will promise to shut up. And we'll go through examples of this stuff. Very similar to this, let me just mention the second type of equation that we can have. Oops, I need to do something here. Okay. The second type of equation that we can have of a line is called a parametric equation. All right. Now, that really comes directly from the vector equation. Comes directly from the vector equation. Let's say our direction vector v has the components a, b, and c. Let's suppose our point on the line that we're given, point on the line, r naught, is this position vector x naught, y naught, and z naught. So all I'm doing now is giving individual components to this vector equation that I wrote up above. And let's say then that our r here in general are the variables x, y, and z. So I can change my vector equation, r equal r naught plus variable t times v. That becomes this. The vector x, y, z equals the vector x naught, y naught, and z naught plus t times the direction vector a, b, and c. I'm just basically expanding out the vector equation. And then what can I do here? I can take each individual component here and set it equal to each other. So I can say from this that our first component, x, is going to equal our x naught from our single point plus our variable t times a, or I could write that a times t. Similarly, our second component, y, equals our second component of the point, y naught, plus our variable t times the second component of the direction, plus b times t. And I do the same thing with z. Z is equal to z naught plus t times c, or c times t. So what I get here then, I end up with three equivalent equations for our line. One for x, one for y, one for z. These are called parametric equations because they have the parameter t that's common to all three of them. Notice that the a, b, and c here come from the direction vector. The x, y, and z naught come from the single point. All right? Okay. So thanks for bearing with me on that, and we'll continue with this next time.